Okay, so let's continue with the summer school. And today we have, so now we'll have the fourth lecture of Professor Sophie Morier-Genoud. So please, Sophie.
Yes, so thank you. Do you see the
Yes,
page?
yes,
okay.
Yes, it's 100% full, yes.
Yeah. Okay, as I said earlier this morning, so for this last lecture, I want to go back on things that were kind of left on the way. So at some point, we mentioned the Hirzebruch formula. So I'm gonna go over this formula again, and also what was not said from the beginning is the origin of the frieze, the motivation of Coxeter. So I will discuss a little bit geometric picture related to frieze, and go also over the modern developments. Okay, so let's go back to this Hirzebruch just to refresh the mind. I go back earlier in the course, and Hirzebruch appeared here. Maybe not very well written, but so what was the Hirzebruch formula? So at this time, what we said was that if I make some counting on this picture, on the triangulation, the rational number that I can compute with a sequence of A's that counts a triangle, the sequence of triangle with base down, triangle with base up. So A1 triangle down, A2 up, A3 down, and so on. If I plug in this number in a continued fraction, I get a rational, and that's the same rational that I get if I compute with a negative expansion from the quiddity sequence. So in this picture, I don't need the full sequence, I just need a part of the quiddity sequence. The triangulation has two exterior triangles, so their quiddity number are 1 here, and I just need the sequence between these two ones. Okay, but it was a claim why this is true. So if this is true, we can write down an explicit formula, because we can just from the picture realize what is the connection between the A's and the C's. So we did it the first day, and I kind of wrote, but for here corner how to get to the explicit formula. So of course, if you want the explicit formula, you can check that this is exactly this combinatorial interpretation. So we need to check something behind. So that's what I want to do now. Okay, so go back here. And so here the book formula. I repeat again. I write between brackets the sequence of A. That means that I'm considering a number. I'll put it this way. So this gives a rational number that I can also expand with another type of continued fraction, and so on, CK. And for this expansion, I write the sequence of C between double brackets. That's the notation. for this fraction. So another link that we want to, so what we have claimed earlier is that this number, this represents a number, a rational number, and the negative expansion is obtained as follows. It's A1 plus 1. Then I write a sequence of 2's, A2 minus 1 times. Then I write A3 plus 2, and then a sequence of 2's, A4 minus 1 times. There will be some collapse here. Let's move. And so on, up to the end, A2m minus 1 plus 2, and then a sequence of 2, A2m minus 1 time. Okay. And actually, this formula may be understood in another language. So we want to understand this. And so this formula may be understood using group theory, I mean, using the group SL2Z as a change of generators in the group SL2Z. So the group of 2 by 2 matrices with determinant 1 and with integer entries. So the problem of conversion of fractions is the same as the problem of change of generators. So let's go in the group SL2Z. We already used matrix in SL2Z, so that's the same actually matrices that will appear. So I call T this transvection matrix. I call S as this matrix. And I'm gonna use also L, the transpose of T. And it is a very well-known fact that any two of these matrices form a set of generators for SL2Z. SL2Z are generated by either T and S, or T and L, or L and S. So I will only need L and T. Okay, so what happens is that if I compute this product, so sometimes to make things easier, I can maybe to be on the safe side, I should use the PSL2, meaning that I'm working up to a sign. So it's very nice to work up to a sign, so you don't make sign errors. So for instance, in S squared is minus identity, but in this group it becomes identity. So I can consider S as having order 2. So that's where here when a general product, a general element, a general decomposition would need to use T inverse and S inverse, but I don't need to use S inverse because it's almost S already. And so anyway, so what I'm doing here is I'm looking at such kind of product in SL2. This gives a matrix. I don't really bother about the second column, but that's cool. It's also a fact, easy fact, actually it's on the exercise sheet, that what you have in the first column, the ratio of the first column gives you the rational with continued fraction expansion C1, C2, Ck. So to be on the safe side, it's better to start with a rational, to look at this decomposition and to compute this formula, because if you start with arbitrary number here, maybe this could have no sense, because maybe you are dividing by 0 at some point. So the matrices are kind of more flexible. You can have zeros in the matrix in the second row, but you cannot have 0 in the denominator. So it's a better way to understand this kind of continued fraction, is to understand them as a product of matrix. It allows more freedom. Okay, so if T and S are generators, I mean, if L and T are also generators, so that means that this matrix I can rewrite as a product of T and L. So I should be able to rewrite this matrix as T A1, L, A2, T, A3, L, A4, as a product of T and L up to some A2M minus 1, L, A2M, and maybe, okay. So again, some power of T here. So if you, sorry, maybe I should mention this. It was on the exercise, but maybe you had no time to look at it. So let me mention that this product of these two gives you exactly this C1 minus 1, 1, 0 matrix. So when you compute this product, this is exactly what was called M of C1 and Ck. Okay, and here, if you compute the product of these two, you will have A1, 1, 1, 0, A2, 1, 1, 0. So I'm not saying that T to the A1 is this matrix and L to the A2 is this matrix. This is wrong, so I'm not saying this. These matrices have determinant -1, so it's not individually this matrix and this matrix. But the product of these two is the same as the product of these two. So when you go all over the sequence, this green product also computes the rational PQ. The same rational. I mean, okay, I don't need value here. So the continued fraction with the negative sign is a product of elementary matrices with a negative sign here, and the continued fraction with the regular continued fraction with the plus is a product of the same matrix but with a plus here. So this link between continued fraction and product of matrix is very easy. So if I compute, so if I have this rational given with these two expansions, if I compute this product of matrix in the first column, I have P and Q. And if I compute this product of matrix in the first column, I also have P and Q. But these two matrices, if they have the same first column, then they are the same up to a multiplication by T. Okay, if you multiply this matrix by a power of T, you don't change the first column, you change the second column. And with a good power of T, you will be able to find, to make the two matrices coincide. Okay, so now what do I need to understand the Hirzebruch formula is just to make computation to make matrix computation. So lemma. So I'm not going to check the lemma. Yes.
Excuse me, Sophie, could you please take a look at the chat? There are a couple of questions.
Okay. No, sorry. It's because okay. So first question: the R and S in the column, in the first column. So I am asked what is this significant? So R and S, it's actually, it could be better to use a negative sign here and to say that RS is the rational number that you count when you stop just one step before the end. So the significance is that you have a rational computed with the same sequence, but just shorter. So that's the answer for one of the questions. Sorry, here I did not know what letter to choose. Maybe I'm gonna choose the star has no meaning. It's just that I want a power and I was out of letters. I could not use A, B, C, P, Q. I don't know what to use. So let's use an L, an integer. So what I'm saying is that I can adjust this power to make sure that this green product coincide with the blue product. Okay, because I already know that they have the same first column. And okay, so these are also letters that's so this is not R and S, it's something else. So let's call them T and U. But I don't need all these letters, that's why I want. And if I call them T and U, that's the same. T and U is the rationals that you compute, but with one step less. Okay. And so this number is not the same as this number, but it's a combination, easy combination. It's arithmetic. You need a Bezout theorem in arithmetic to understand that applying some multiple of P in T and changing U with a multiple of the same multiple of Q, you can produce this number. Okay, anyway, don't really need to pay attention to the second column. So the lemma to finish, oops. The correspondence is to compute. So you can compute that. There was another question, sorry. Why is L raised? So I said that I don't need the power of S because S squared is minus identity. So I may only consider S without any power. But here to produce this matrix, I really need to, that's what I will have with T to the A1 and L to the A2. This will produce this, this product of two matrices. And L and T are not, have not finite order in the group. They go to infinity. So I really need to consider L with a power. Yes, there was another question. To answer the last question, you can also say that this is L and S. But L is somehow just a transpose. So if you, L is the transpose of T. So when you do something with T and S, it's the same as doing things with L and S up to transposition of matrix. So I don't need this set of generators. Okay, so what I want to say is that T to the power L it can be written as the matrix M, or negative minus M of A plus 1, 1, 1. This is the notation M of something, M of a sequence is this product. So it's just, you check this just by computing matrices T to the A, that this matrix with an A here. And now it's a product of 3 elementary matrices that you have to multiply, and you multiply 3 matrices, and you just have to check that you get T to the A. So it's just immediate checking. So I'm converting, okay, so T to the A. So now I need a similar thing for T, L to the A. So L to the A, if I want to write this as a matrix M of something, it's M of 1, 2, 2, 2, 1, 1. And here I need A2s. So this checking is also matrix computation that you can do by induction, okay? Because there is these dots. You have some dots here, so the best is to use an induction, and it's really also immediate by induction to prove that L to the A can be written as a product of elementary matrices of this form using the sequence 1, 2, 2, 2, 1, 1. Okay. And what else do we need? We need to notice that M of 1, 1, 1 is a minus identity. And that's the frieze of width 0. But we need also to know that if I compute 2, 1, 1, and a value A, it is the same as the matrix M. No, sorry, I'm going to A plus 1. And this is the same as negative M of A plus 2. So again, just checking. You take these 4 coefficients, you compute a product of 4 matrices, you have a matrix which is exactly the same as this one. So I don't go over the proof of the lemma, just. And so the formula, no. So to get, here's the book formula. So you just need to make this change in this product. You know that this product, you're gonna try to rewrite this product as a matrix M of something. Okay. And so you just have to concatenate. So this first matrix, T of A1 is gonna be something like that. So I'm gonna work up to a sign, but for a moment. So when you compute TA1, LA2, and so on, what happens is that you have the matrix M of A plus 1, 1, 1, times M of 1, 2, 2, 2, 1, 1. But this means that you are concatenating, that you have the matrix M over the sequence of these numbers. But each time you see 3 ones in a row, this simplifies to minus identity. So somehow, when you concatenate these two things, the sequence of 1 will disappear, and you will get only A plus 1, so A1 plus 1, and here it's A2 times. But the ones disappear, so you only have a sequence of 2s, and then a sequence of 1. But because you have to again add some A3 plus 1, 1, 1. So now you will have to concatenate with A3 plus 1, 1, 1. And what's going to happen is that here, this sequence will simplify using the lemma. Using the lemma, when you have a sequence 2, 1, 1, A plus 1, you can reduce to this shorter sequence. And so that's exactly what will lead to the Hirzebruch formula. At the end, this product of matrices is going to be the products of so M. I mean, that's what we wanted. So we will have A2 minus 1, 2's here, and then we will have A3 plus 2. So the plus 2 comes from that when I shorten this sequence, the coefficient that here increased by 1. And then again, I will have a sequence of 3 ones in a row that I will forget. And this will restart with a sequence of 2, A4 times, and so on, and so on. And this is the conversion. Does this make sense? I'm gonna try to see if there's a question in the chat. Okay, there is no question. Fine, okay. Okay, so let's just move to different story. And what I want to discuss now is some geometry related to Coxeter frieze. And it's actually, so frieze are actually an invention of Coxeter. It was a way to organize relationship between numbers in some geometric pictures. So let's try to explain or to show at least what kind of geometric objects are related to frieze. I have prepared a picture. It is this one. So what do I have here? I have drawn what is called a pentagram. This picture in the plane is called a pentagram, but here it's drawn on a sphere. And it's drawn on a sphere so that we have two conditions. So these arcs are grid circles, are pieces of grid circles. Every arc that you see, they are drawn on a grid circle in the sphere. And what you need to know is that here, everywhere we have right angles. I don't know, I would write this symbol to mention that these are right angles. And the pentagram, the picture is determined only by this triangle. If you start with this triangle, there is a unique way to extend the triangle to have this picture. And so it was a long time ago in the 16th century or something. There was a natural question to understand if one can find the analog of Pythagoras theorem. So if you have a right triangle in the plane, you know how the lengths are connected in Euclidean geometry. And what about the lengths in spherical geometry? What can be said about the length of a right-angled triangle drawn in the sphere? And it's, so there is an answer, but what is nice is that it's to study the entire pentagram determined by a right-angle triangle. And there are relations between the lengths of these arcs. So there are 5 arcs. That's alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 are the lengths of these arcs. So the sphere is a unit sphere. And if you compute Ci to be the tangent of alpha I square, what you will have is that these numbers will determine a frieze. So this time we don't have any more integer in the frieze. Okay, but so this is a frieze. And somehow it's just the frieze becomes just a way to organize the relation between these numbers. So these numbers come from the geometric picture. They are not free numbers. They cannot take any 5 values that you want. They have to have relation between them. And the relation is exactly that C2 times C1 minus C4 is 1, C4, C5 minus C2 is 1. And so it's a way to encode the relation Ci plus 1 equals 1 plus Ci plus 3. And actually, I don't know if it makes sense, but if you think about it, so these numbers, they can be thought cyclically, okay? C1, C2, I can call C6. There is a cyclic symmetry here. So this is true when I consider the indices up to modulo 5. And this cyclic symmetry of the picture is equivalent of the periodicity of the frieze. So because these numbers come from this symmetric picture, this sequence has to be 5 periodic. So it's something sometimes called as the Gauss map. So what I'm saying here that you can deduce that if you have a sequence Ci of non-zero numbers such that they satisfy this recursion, then it is 5 periodic. So that's something pretty nice that can be understood with or without frieze, but it's this is a periodicity or the glide symmetry in the frieze. If you have a sequence like this, you write it in the first row of a frieze, in the second row of the frieze, because you know that this is true. Here you first write by C6, C7, but the glide symmetry in the frieze imposes that these 2 values are the same. Okay, so the periodicity is the same as the periodicity in the frieze. Okay, I don't know really how to check this. I mean, one has to be kind of comfortable with the spherical geometry. But let's say it in another language again, another geometric language, which is the following.
Can I just interrupt you for a second? For the previous one, there is equation, but these
yeah,
aren't necessarily integers.
No. So this time we have a, no. So this time we are looking at frieze over positive numbers. Frieze over, okay, no. We are not considering, so I'm talking about frieze in a more general meaning. Okay, sorry for the confusion. Maybe I move this. Okay, so the second picture I want to show is the following. So this picture is a choice of points on P1. So this time I can also work over C, for instance. And I'm going to talk about frieze over C, or frieze over. So here you can choose R or C, real numbers or complex numbers, but this time not necessarily positive. What we have here is a choice of 5 points on the projective line, which is the same as 5 lines in the plane. And we want to consider this configuration of points modulo the action of the projective transformations, PSL2 or over R. Yeah. Maybe you know that if you choose 3 lines, you can always send 3 lines to 3 other lines, 3 distinct lines to 3 distinct lines by a matrix of PSL2. There is a transformation that changes 3 lines to any other choice of 3 lines. Starting with 4 lines, it's not always possible. If you have 4 lines and 4 lines, maybe there is no matrix that goes from one set to the other. What you need to check is that if they are the same cross ratio. So it's the invariant for this problem. And so when you have 5 points, if you want to consider these 5 points modulo a matrix of PSL2, or if you have 5 lines modulo PSL2, you have 5 cross ratio to check if you want to send 5 to 5. So let's introduce the notion, the cross ratio. So let's suppose that you have C1, the cross ratio over, let's choose vertex 2, vertex 3, vertex 4, vertex 5. Let's call C2 the cross ratio over V3, V4, V5, and V1, and so on. So you cyclically change the order. So up to C5, that's going to be the cross ratio between V1, V2, V3, and V4. There are several formulas that you can use for a cross ratio. So the one I want to use is this one. Which one? V1 minus V4 times V2 minus V3 over V1 minus V2, V3 minus V4. So if you look at this 5 cross ratio, they are not free numbers. You cannot assign 5 number at random. The relationship between this 5 cross ratio, and the relation is again the relation of a frieze. And again, the cyclic symmetry of the problem explains this glide symmetry here. And this can be generalized, and actually it was kind of the starting point of Coxeter. So this was noticed by Coxeter, and the idea was to understand what happens if we have bigger arrays. Do we still have this? Sorry, there's a question. They are complex number. It's a fine coordinates on this line. So I consider the VI like a complex number. So it's because I chose C here, but non-zero because the points are distant. I did not say it, but I want the points to be. So so the idea of Coxeter was to understand if this periodicity that can be understood here, this is true for bigger arrays, or in other words, can we understand more relations between the cross ratio when we have more cross ratios? And this leads to a connection between frieze and a famous space that's one called the moduli space M0n. So this is the set of tuples, n tuples of points, distinct points, modulo PSL2. And for n equals 5, that's the same as frieze of width 2. And this is true in more general settings, that this, when n is odd, this set can be identified with the set of frieze. So, see, of width n-3. Okay, so this is a geometric interpretation of the frieze. That's the same as the space. Okay, we have maybe 15 more minutes. And are there any questions about this geometry? Okay, so let's talk about more frieze. So as I said in the first talk, this Conway-Coxeter paper went unnoticed, and it's starting from 2005 that there was a revival of frieze due to connection with cluster algebra. And frieze were linked to quiver representation, to moduli space, and so on. And there was a new interest. And also, I'm maybe really sorry for this comparison, but it was like a virus, like a coronavirus. There was a lot of variants because of these beautiful properties that one were able to find all the time. It gave the idea to change a little bit the notion of frieze. So let me go over what you can do. So you can change the rule, of course. The initial rule is A, B, C, D. You want in this configuration to have this. So let's change what can be done. Why not using other operations? sorry, I'm gonna write maybe the other way like this. AD is BC plus 1. So I don't even need a subtraction. I said at some point that the rule makes sense when you are over a ring, but you don't even need to know how to subtract the numbers. So for instance, you could use tropical operation instead of, so you could use a semi-field. For example, A plus D would become, the rule would become A plus D equals mean of B plus C and 0, or 1. I mean, you can change, and this would lead to tropical frieze. And this has been studied recently. So there is a notion of tropical frieze. You could remove this mean and just look at a rule like A plus D equals B plus C, and this would give you a additive version of frieze. This is also studied in the literature. There is a suggestion also to use the NIM addition. I don't know if you know what it is. So just, and every time people come with a new version of frieze, there is always something very interesting from the viewpoint of combinatorics or geometry. And for instance, with this rule, we always have the periodicity and the glide. So you can change the operation, you can change the number. You can work with the finite fields. And now everything becomes finite. You can try to count how many frieze you have when you fix a field. You can, what can you do? You can, there is another rule, you can change a little bit the configuration, add a number here and ask that AD minus BC equals the middle value. So this is a notion of two frieze that has been studied. What can you do? You can remove the boundary condition. We say that we want the frieze to start and end with rows of ones, but why do we want this? We can remove either one of the row, the bottom row, for instance. You will get infinite frieze. Or you can remove the two boundary condition, and what you would get is a SL2 tiling. So I'm just writing keywords of things that have been studied recently. And of course, you can also extend this rule. Here we want that these 2x2 matrices in the array have determinant 1, but you can take bigger square, and then you can go to the notion of SLK frieze. And you can work over Z or over C. And this will give you the analog of the space, but with in higher dimension. If you remove, if you take k minus 1 here, if you have pk to the k minus 1, this will lead to the notion of SLK frieze. Okay, and so as I said also that, so this connection with cluster algebra is because the frieze rule is the same as a mutation in the cluster algebra, or that can be produced from a quiver. A quiver is an oriented graph. So you can also change the quiver and get more frieze. For example, there is a quiver that gives you the Markov numbers. So anyway, so it's just some overview of what can be done. And maybe you will find something interesting to study along these lines. So I think I'm going to stop here. So thank you for your attention.